Okay. Hey, people. Robert, can you hear me? You can write in the chat. Okay, very good. Sound quality, 1, 2. Okay, perfect. So today, visiting yet once again rotations, like as if we didn't have enough, a bit more rotations. C, because there is really a lot of going on, and B, because it will really help us when we'll get rotation in 3D. So that will take us about 5 minutes, and then we are moving into sampling and colors and aliasing and image enhancement and a bunch of other stuff that is waiting. Questions about anything? Perfect. So you saw that Amir published also snippets of code that does matrix multiplication, and he will put a video on how to use it. He was supposed to be here today to give a little demo about if you want to use libraries that he gave to do matrix multiplication, working with vectors. You can use these templates. If you want, you don't have to. Yeah?
Is there an issue if we do that ourselves, even if we don't make it like the most general?
Absolutely not. But it's no, definitely not. I mean, it needs to run. How do you get it to run is as long as it's according to the spec, no issues. So you can use a template that you'll use about here are vectors, here is a matrix, here call matrix A by matrix B, because you never need to know what are these matrices. Right? You just tell it multiply translation matrix that I know how to write times multiply rotation matrix that I know how to write. I never care about what the numbers that pops up from this multiplication. Other questions about? Okay. And maybe I warned it you, but I warned one of you. Well, you're generating a bunch of frames, and let's say that every frame is rotation by 15 degrees. Again, the first frame takes the original image, rotate it by 15 degrees. Now, how do you generate the next image? You can take the intermediate image and rotate it by 15 degrees, and each time rotate by 15 degrees, which will look quite crappy each time that you're doing, because you're adding noise every time that you're doing it. Or at the second frame, where you're rotating by 30 degrees, go to the original image and rotate it by 30 degrees. Instead of rotate the intermediate image by 15, go to the original, rotate by 30. And the third frame would be rotate by 45, and so on. So you're only changing the values of the cosine sine in the rotation matrix. OK, one more way to talk about the rotational matrix that by now we all remember that the rotational matrix is cosine theta minus sinus theta, sinus and cosine. And how are we thinking about matrix multiplication? We can think about the matrix multiplication in two ways. We can think about the matrix multiplication as here is one row vector, R1, another row vector, R2, and I multiply it by some other vector, say 1, 0, that is by this point, and I do dot product with the first line, dot product with the second line. We can think about this product in this way. But this is also equal to, let's take the same element of the matrix and think about them as two vectors, column 1, another vector, column 2, and now when I multiply it by 1 and 0, I create linear combination of these two vectors. I take the first vector, multiply it by the first constant, let's say alpha. Let's call this number alpha. Let's call this number beta. And what I do is create a linear combination of the first vector, C1 times 1 plus C2, the second column vector, by 2 times 0 in this case, or in general, C1 times alpha plus C2 times beta. So this creates this linear combination of these two vectors. Now, let me remind you what are bases that you might have heard of from linear algebra. If I have a few vectors, u1, u2, u3, u4, I can create all the linear combination alpha 1, u1 plus alpha 2, u2 plus alpha 3, u3 plus alpha 4, u4, where alpha i's are real number. What do I do by taking all the linear combination of these vectors? Well, then I'm creating a subspace that these vectors span. Let's try to be a bit less abstract. If here is u1 and here is u2, and these are the two vectors, both lives on the whiteboard, and I look at all the linear combination of the form alpha 1 u1 plus alpha 2 u2, where alpha 1 and alpha 2 are both between 0 and 1. Every combination of these alpha i's, when I do this linear combination of the vectors, creates a point somewhere, a vector somewhere that is alpha 1 scalar times the vector u1 plus alpha 2 times the scalar of u2. Where the scalar, remember, just takes a vector and make it longer or shorter. And if it's negative, also going backward. So what's the shape that I'm creating right here? Alpha 1 u1 plus alpha 2 u2, where alpha 1 and alpha 2 are both between 0 and 1. Just like 2D? Yeah. It will be used the moment that I'll remove the limitation that alpha 1 is between, I'll write it larger, In this case, it was alpha 1 is between 1 and 0, and the solve goes for alpha 2 is between 1 and 0. It will be, it might be a square. It's a bit more general. Let's take the case that alpha 1 is let's ask what is, let's take the case that alpha 1 and alpha 2 are both 0. Then I'm just getting the origin. Alpha 1, U1 are both 1. What do you get? Take U1 and copy it over here. This is also a copy of U1. I can also get to the same point. This point is U1 plus U2. And I can also get to it by adding U1 plus U2 from the other direction. So that was when alpha 1 and alpha 2 are both 1. What happened when I let them go crazy between alpha 1 and alpha 2? The shape that I'll create will be a parallelogram. But everything around here, you can create all the points in between by choosing values of alpha 1 and alpha 2. So in particular, if U1 and U2 are orthogonal to each other, it will be a rectangle. And if their length is 1, it's actually a square. If now I remove, what happens if I'll go back to this location, this restriction, and I'll remove one side of the inequality? So alpha 1 and alpha 2 still needs to be positive, but they can go as long or as large as you want. What's the shape that I can create by all the linear combination? So I take all the linear combination of alpha 1 as before, U1 plus alpha 2, U2. U2 is this vector, U1 is this vector. Maybe the length is 1, not necessarily. And I just have two nested loop. For alpha 1 goes any value that it wants as long as it's positive. Alpha 2 picks any value that it wants as long as it's positive. And yeah. Not yet. Yeah. I mean, if U1 and U2 are both on the whiteboard, then the linear combination will be inside the whiteboard, will be in this plane, in this subspace. But if the coefficients are both positive, nobody? Yeah, it will. Yes, yes, it is. Let's keep alpha 1 to be 0. And I just change alpha 2 to be any positive number. What's the shape that I'm creating? Alpha 1 is 0, so it's only alpha 2 times U2. Sorry? extending U2 and make it array. That will play a lot when we'll do ray tracing.
Couldn't it also be negative
Sweet.
but backwards still?
Not if I impose this constraint. When I remove this constraint, then I'll cover the whole plane, absolutely. U1, I'll keep alpha 2 0, and I'll just let U1, alpha 1 to change. So U2 is not in the game. U1 covers all the points along this line. So this way, alpha 1 U1 is like the extreme case where the coefficient of U2 is 0, and vice versa. So now if they can both be anywhere they want, as long as they are both positive, yep.
Creates, I guess it's not quite the span, but all possible values in that parallelogram.
Yeah, I don't know if it's okay to call it parallelogram because its other boundaries are far, far away at infinity, but it's called, people, what's the name of this geometric shape that it creates? Again, so far we identify one way that goes to infinity inside this shape, another way that goes to infinity inside the shape. Let's practice with another example, with another case. Where is alpha U1 plus the very same alpha U2? And alpha is any positive number. So here U1 and U2 are identical. So here U1 and U2 are these two vectors, but I multiply both of them by the same number.
Create a triangle?
Is the case of alpha equal half. It's included in here. Where is alpha U1, where is U1 half and U2 half? U1 half plus U2 half. It is just in the middle of the way between U1 and U2. And now when I change, so I created this vector. That was when alpha happens to be half. When I change alpha, I included in my shape this line. OK, so to say that it's parallelogram, it's, I don't know, it's mostly OK, but, because the boundaries are somewhere in infinity. So this shape over here, it has a name. It's called the cone. Every infinite set of rays. And that happens when alpha 1 and alpha 2 are only positive. Since we are already in this game, and since it's very important for this course later, you tell me again. Let's redraw. Here is U1. Here is U2. And now I considered alpha 1 U1 plus alpha 2 U2. But that's called convex combination. Hint, hint. Convex combination of U1 and U2. It will be very relevant in multiple points in this course. What's the shape? We had the case that alpha 1 and alpha 2 can go anywhere from 0 to 1. And now I'm adding on not only that are going between 0 and 1, but their sum should be exactly 1. What is the shape that I create?
Kind of a circle.
It's an oval.
Mm,
It's not square.
it's, no. Alpha 1 plus alpha 2 is 1. So, yeah.
Oh, aren't you just adding the vectors to like u1 and u2? It's just u1 plus u2, so it'd just be a
As a set of points, it will be.
Is it a line between the two?
I'm very obnoxious about lines because lines go where in my world, lines is something that goes from infinity to infinity. Line segment that goes between. Exactly. You're adding this part. Everybody agree? I'm just giving weights to, here I'm giving all the weights to u1. Alpha 1 is 1, implying alpha 2 is 0. All the weights is at u1. When alpha 2 is 1 and alpha 1 is 0, then all the weight is at u2. And you can check if it's half and half, then you're just on the middle of the way between them. So in this way, you can generate this segment. Agree? I just generated this segment. Last one. Alpha 1 plus alpha 2, the sum is less or equal than 1. Want to remind you, when without this constraint, but with this constraint, then we had a parallelogram. That it was a copy of U2, that was a copy of U1, and when I ignore this, I created the whole parallelogram. When I add these constraints, that the sum is less or equal than 1, then I'm getting the whole triangle. And since we'll have many, many triangulations and triangles and linear interpolation between vertices of the triangulation all over the case, all over the course. It was time well spent. Okay, and of course, if I let u1 and u2 go get any values that they want, then they cover the whole the whole 2D plane. And if I have 3 vectors, then most likely they will cover the whole space, unless my 3 vectors are all living in a 2D or a 1D case. If I have any 3 vectors which are linearly independent, none of them could be created as a linear combination of the other 2, then they cover the whole space when I let them play. And what I hopefully showed you so far is that I can think about the rotation matrix as if I want to say that when I rotate, look at the point C over here, and after the rotation, C will be going to some new point, C prime. And I want to pretend that I don't know exactly how, but for some point, C prime would be C times some matrix. And I want to understand how to build this matrix. Okay, the same matrix that we saw before. And I want to build this matrix so that if C is understood as a linear combination of elements, then the rotational matrix will take linear combination of, it's becoming a bit too abstract. Let's get back to it. So what you see in this template is that I have ignored the red vectors. I have one unit vector that goes to the positive x direction. I have one unit vector length 1 going in the y direction. And now thinking about a point C over here, whose coordinates are 0, 7, 0, 4, or alpha and beta, here, C, which usually I write alpha and beta, I'll tell you, you know what, you can think about these alpha and beta in the very obnoxious, complicated way as follows. It will be alpha times go in the x direction. Go in the x direction, how many units? Alpha units towards the x direction. Start at the origin, and now go in the x direction, alpha units, 0.7 units, and whenever you're getting to your destination, go in the y direction, add to it in the y direction, how many? Beta units. Okay, that's just was a very complicated way to say what is alpha and beta. And now I want to imagine that if I'll just think about the white matrix M, and I multiply M by alpha x plus beta y, I will get something meaningful. I will get C prime, which is a point. I will get C prime, which is where not C, but C after this rotation. And this matrix should not be, depends on what are these points. Should not depend on what are alpha and beta. It's one matrix that just depending on by how much I rotate, what is theta. But if this is a linear transformation, right? It's multiplication by a matrix, does some linear things. What is a linear thing? You take 0 to 0, and when you multiply it by the sum of two objects, it's like multiplying by the sum by the first one plus multiply by the second one, which makes us what? Alpha times m of x vector plus beta times m of the y vector, just because it's linear product. And that actually makes sense, because what does it tell me? It tells me that after rotation, let's forget the point C for a moment. Let's ignore C itself for a moment, but I do want to think about the x vector and ask, what happened to the x vector when I rotate my world? I rotate everything here counterclockwise by theta. The x vector will end up at a new vector, x prime. This x prime is exactly what should happen here. This should be x prime. Same goes for y prime. How can I get to the point C prime, to the point C prime that I'll generate? Before rotation, I told you go by alpha along the x. Now x has moved to the x prime, so just go by the same alpha, but not toward x, but toward x prime, but by the same amount. Go by alpha amount to the vector m times x prime, the new vector of where x used to be after the rotation. And once you have done it, here is the original C. Once you've done it, go by alpha to the x direction, and once you get to your destination, go in the y prime. What is a y? What is y prime? Original y rotated. Go in this direction, beta units. So all I need to do is just to compute what is alpha and beta. What is x prime and y prime in this scenario. But at this point, I'll show you exactly the numbers, but let's remember also why it makes sense. We think about the linear, about multiplying by a matrix, as we said. We can think about multiplying alpha and beta as take alpha and beta and multiply the first column, the first row, and multiply the second row, dot product. Or let's use the other way to think about it, as multiplying it by the first column. That is, think about it as take the whole first column, multiply it by alpha. C1 multiplied by alpha plus take the second column, C2, plus second column, C2, and multiplied by beta, and takes the linear combination of these two vectors. So that's pretty cool, because all I need to do now to understand the rotation is just look at this new vector, y prime, and ask, how do I express it in the xy coordinate? Why is this so cool? Because it will tell us that in 3D, when we have 3D rotations, it will be kind of unpleasant to start expressing rotation from here to here as a rotation by x, rotation by y, rotation by z. It's always a no possibility, but it will be kind of unpleasant. It would be much easier to just figure out what are the vectors in each direction, and just say, now when I know what are the vectors, let me write them as column vectors. Let's write a matrix of these column vectors, and that does the trick for me. That's a rotation. For example, if I tell you that I want to we had this exercise, the house over here, and I want to flip the house around this line, when I'll care about the rotation, if I have a vector that's going in this direction, I'll just generate another vector that's going in the other direction, express both these vectors in the coordinate system, and then I don't need to worry about to compute arc tangents or cosine of this angle. I never care what this angle is directly. OK, so we are almost done. Let's just write what happens to the x-axis after the rotation. What are the coordinates? The length of x is 1. I rotate it by theta. The x-axis rotated by theta. What is this point? This divided by this is cosine theta. And this divided by this is sinus theta. It's in front of the angle. The length of x prime is 1. So this is just sinus theta and cosine theta. OK, that helps us. That's how we express x prime. What about y prime, which is y after rotation? Its theta is right here, because both x and y rotated. So y prime is somewhere here. So its y coordinate, the height of it, is just, this is essentially this. This triangle is this triangle. So its y, the length of its y, is cosine. What about the y? The length of this y is minus sine, but which direction is this going? Going negatively. So it's minus sine theta. Fine, so let's did I figure out that x is going to be, the new x is going to be the new column vector. That's going to be the new x prime, which is the new x after the rotation, whose coordinates, its x and y coordinates, are cosine theta and sinus theta. Well, I'm looking at the column. Earlier I was looking at the row. Now I'm looking at the column and I just write, hey, this is a vector, that's its coordinate. Which vector? X prime. Similarly, what are the coordinates of y prime? Its x value, its x value is minus sinus theta. Its y value of y prime is sinus theta. Okay, that's a new.
Isn't it cosine?
Probably. Cool. Excellent. Okay. So we got to the same rotational matrix, but that's the only method that will make life easier in 3D. Think about it. In 3D, it will just be express u, v, w in the xy plane, and you immediately are getting your rotational matrix. It's going good. Okay. So it's a combination of a few lectures from the original and covering several topics, talking about lights, waves, wavelengths. Our sign, here it is wavelengths. Speed of light, quite fast. Wavelength, we are poor, pathetic creatures, see only tiny little spectrum of their all wavelengths between these set of wavelengths for a point to make when we can refer to a wavelength and say that's its color, but usually when we are saying color, we mean some combination of wavelengths. But yellow will be the addition of several wavelengths. Just to distinguish between color and wavelengths. Okay. Several sensors in our eyes. Okay, depending on the wavelengths that they are sensitive with. Hunters, probably the way that their eyes are built, are very good in identifying very small amount of light, especially if they are hunting at night. What happened to it? We, maybe, rather well, care for the wave, care very much. On the colors, less sensitive. At the night, very, very sensitive to shades of gray, shades of green. So a lot of our sensors are dedicated to identify greens, which values of greens. 3 types of cones in our eye. That would be red RGB, which is why we can be fooled by by looking only at pixels that create RGB. So we have these 3 types of cones plus another type of cones. We'll get to in a moment that is very good in identifying little amount of light, but doesn't show much sensitivity to which frequencies this light is. And we are not, as animal, we are not particularly sensitive. Not particularly sensitive. 12 types of sensors for this amazing creature. By the way, look it out, amazing creature from so many ways, not only because of the eyes, but also 12 types of color sensitivities. But mantis shrimps, really, really fantastic animal. And again, I'm not trying to make this course about the perception side. That is a huge, huge area of what do we understand as color versus what is the physical side of the color. It's a huge area, and we will definitely speak about color correction, like gamma correction that we'll talk about, but I'll talk less about what is our understanding of this side. Okay, color model, abstraction of the mathematical system that represents the color, which is very different than what do we understand as this color. Well, we have 3 types of receptors, so we can be cheated by representing 3 numbers or 3 main colors. And how do we arrange these colors? RGB is one option, but not only, depending on how do we create the colors out there. See in a moment. Okay, gamut of colors. What is the range of all the colors of the color model? Now, when we're talking about RGB, what do we think about? We think about the background that is actually black. The background here emits no light. If R equal G equal B are 0, it means it emits no light at all. Each pixel blocks light that's sent behind it if you're talking about LCD. And then you are adding to it one of the colors, red or blue or green. And by doing so, you're creating all the combinations. And we can be cheated enough so that once we are getting enough signal from all 3, we'll call it white. Okay, what about pointers that start from, what do pointer doing? Sorry, I'll get back to the cheating part. What do pointer doing? I take a white page, and on top of it, I put some color, and this color that I just put here, what happened to the light? Let's pretend that the light goes from the lamp, that is sun, white light, bounced from the page. The white light that contains all the frequency bounced from my page and reflected, and now when I placed this, it's white, but you wouldn't see it if it's white. Then it's once I put red over it, it means I prevented the red color from going. So what will you see as the color over here? It's everything beside the red filter that I placed on top. So I subtract from the white. putting a cayenne color, I subtracted, or putting the blue color, I removed from the white blue. So I'm left with magenta, I think. I removed from it, we'll see in a moment. If I'll remove everything, both the cayenne plus magenta plus yellow, then I'll get the light, which suggests a very simple formula that tells me how from the RGB I can go to the CMY system. So we'll talk about the CMY. We'll talk about the CMYK for about 3 seconds. So if we can think about colors, as we said, as additive or removing colors from the overall spectrum, so the overall, wait, this color, sorry, apologize for the slides. Now, when I'm in the CMY, the cayenne would be how much cayenne do I have in the color? 1 minus how much red do I have into it. That is, if you give me an image that is an RGB, and now I'm asking how to mix colors to create this filter, then the amount of cayenne that I want is minus 1. The 100% minus the amount of red that I want. How much magenta do I want? How do I get magenta? I'm removing green from white. What is left when I removed green? Blue and yellow, blue and red. Blue plus red creates magenta. How do I create yellow? I add the RGB minus the blue. You'll get the yellow. Okay, so now from taking an RGB file, you know how to mix colors when you are thinking about filtering, that the colors filter the part. Okay, so that's about the CMY coordinating system, other way to represent color. And sometimes people discover that when they print images, it's all old history for you. I don't know if you've ever seen paper printed, but for printed papers, the paper looks better if you add some black ink to it. I mean, even though we can create black by mixing the RGB or mixing the 3 basic colors that they use, we can make it look more dramatic if we'll add to it new paint that is originally black. So that will tell us how black we want in the whole system. It's not a formula that we are going to use in this course. Just if you've ever seen it. Okay. On the other hand, this is not the latest version of my slides, I'm sorry. Let me. Yeah, sorry. Yeah, light we covered. Isaac Newton played with prisms, shows that the white light from the sun includes all the colors, includes all the basic colors by using prisms, by the way, just created by positive and negative interference because different frequencies need different lengths of the prism to bounce in a positive way where the wavelengths are just fitting and contributing each other, summation on each other, or in the same wavelength plus half the wavelengths, they will just cancel each other. And that's why different wavelengths needs different lengths of the prism when they are bouncing between the 2 sides of the prism, going from back and forth, and each time some part of it also exits, but it's like you see through history. You see the summation of the frequencies plus what bounced in the prism back and forth and then added or cancel the other light. Now, of course, people asked, how do you know that the reason that we see these different colors are because the white includes all the color and not because the prism is painted. So being a smart guy, Newton then take another prism and was able, did I leave this slide alive? Yeah, was able by putting the prism in different way to either generate the whites back together or isolate one of the colors just based on the geometry and so on. So made the point. White sunlight contains everything. We covered this slide, we covered this slide, covered this slide. Hunter, gatherer, oh yeah. Rods and cones, talked about it. Call them the sensors in the eyes. Rods, your night vision placed actually far away from the retina, better to see movement in the night, which is not the direction you're looking at, but at the close to the boundaries of your field. Actually, especially, I guess, when you're not the hunter, then you are the huntee. And the rest of the cones, very biased toward the red cone, green cone, quite an amount. Blue, not very useful, don't need it enough. Very few of the cones. Like, it's really important to know, I guess, fruits and yeah. So this one color model, yeah, just you've all seen this type of tricks. What is darker, this block or this block? Well, they are the same in the same, or this block and this block, well, they are the same, just when we look at them directly, it's just the contrast of other parts that fools us. Many such examples, RGB and CYK. We went through it, the formula of RGB versus CYK. Okay, you can think about RGB as a point in 3D space. HSV, yeah, HSV, or HSL, HSI are close to, and that's definitely worth mentioning. Let's spend a bit time on it. So, cool story where it was invented. So once upon a time, there used to be black and white TVs. It is gray level TVs. And they were there all the time, and then you started to plan. We are talking here about this invention from 1938, but they were already thinking about broadcasting of color TV. And now you think about a transition period where some people will have color TV, but many other people still have black and white TV. So how can you broadcast something for both publics? You can broadcast the same way, or you can take one broadcast that consists only of, for every image, just for every pixel, what is the intensity. But black and white just means for every pixel, what's the intensity of this pixel. And by the way, it's all analog signal. You don't have any numerical processing of the signal. So for the black and white TV, you send just the intensity. Now you want to accumulate something for the people that just bought the new flashy color TV. So it's okay to add something to the signal, but you don't want to make it useless for the black and white owners. So what can I add to the signal that it will make it both useful for the for the color TV, but at the same time useful for everybody that still use black and white TV. So the idea is to look not on the RGB. Right? If I'll send the RGB, only the color TV owners can use it, completely useless for the others. Instead, what we'll do is we'll send 3 signals where the last one, the lightness, the intensity, sometimes it's called brightness, sometimes it's called the value, HSV, HSB, different small differences between them. That's the intensity. If all you have is a black and white color, TV, then for every pixel, that's the only value that you see. What is the other two? They actually nicely arrange the colors in some meaningful way, and here are all the shades of the colors where you can think about one part that red is dominating, one part that green is dominating, and one part, the third of the picture, that blue is dominating. But now you can think about different shades of blue over here, even though it's not formally shade. Different variants of blue, different variants of red, different variants of green. So you arrange it nicely along a circle and give for each point in each sector of this on this circle, you assign it by the degree, somewhere between 0 to 360. Okay. Now, what are the 3 numbers that we send? The saturation, that's a number that tells me if, sure, I know you're telling me that red is slightly more dominant than green and the blue, but by how much is it dominant comparing to them? If it's almost the same, then I'm very close to gray. On the other hand, if I have 2 colors, or 1 color, that are far away from the third one, then I'm very far away from blue. Then I'm very far away from gray. So gray, independent of the intensity, gray will mean R equal G equal B. By some intensity, it can be closer to white, closer to black. How much the intensity of the gray is that I'm controlling with this parameter. How much is one color more pronounced with respect to the others that I'm controlling by the saturation. Where inside this all shape, what type of color will it be? It will be specified by the U. Okay, and it's very useful nowadays. Even if you all don't have analog TV anymore, it's still very useful when we think about color corrections or changing the colors. Because now, if I want to change the intensity, the correct way to change the intensity or to do color correction in my terminal, and you'll play with this in one of the homeworks, will be one of the options will be to express it as these 3 parameters, and if I want to increase the intensity, I can change one parameter without changing what is the feeling toward this color. Make sense? Change the intensity, which we will need. Why we'll need it? Because when we are taking images, usually, well, our monitor can represent somewhere between 4 pixels, somewhere between 0 to 256 in each, 255 in each channel. At most 3 times 256. It's much, much narrower band than what I need when I take an image on film, or as most for cameras. You'll get the minimum and the maximum are far, far away, and you do notice differences between them depending on it. So we'll play with HDR, with how to make the image so that it will look as if you have many levels of ranges of intensity in your monitors, even though we are lying. You don't. Back to the HSV. I have the RGB, just you don't need to memorize it, just to get a feeling about how do we generate these coordinates. Help me to understand how what the numbers in the HSV actually implies. So about the U. about the U, where I am along this big circle, where I am across this big circle. So I look at the three numbers, RGB, and if the maximum among them equals to the minimum, very close to be identical, then it's just gray. And in this case, my U is just not defined. It's gray. And that's fine. Otherwise, let's assume that the maximum is red. So I know that I'll be in the red section. I know that I'll be in the red section of the color space. I need to decide exactly where, and to decide where, given that the maximum is red, I want to ask what is the relationship between the other two colors? How much is green more pronounced than blue? Again, I already know that I'm in the red part. How much is green pronounced more than blue, or blue pronounced more than green? Notice that green might be smaller in its intensity than blue, so this number can be negative. So this number can be negative to make it between 0 and plus 360. In this case, you're just adding 360. So you don't want this whole number to be negative. You want it to be between 0 and 360. So add to be 360. So you're getting a number between 0 and 1. You're getting here between the max and min. Divide this by the difference between the max and min. Okay, that's some number between 0 and 1 multiplied by 60. Give you a section of 120 degrees, exactly as you want. Cool. So in the case of red, you'll be anywhere over here. Okay, and analogously, or if the dominant is green, analogously, the dominant is blue. Dominant is blue, then you ask how much the red is comparing to the green versus green comparing to the red. But you already know it, which of the sections you are. Okay, so that's actually, I think it's very, very clever, the way that these colors are arranged. What about the saturation? Speaks for itself. Saturation, as we said, how close to gray is this? So if the maximum is 0, the maximum is 0, so the saturation is 0. Otherwise, the saturation, how far away? We are just comparing the mean over the max of RGB versus the mean of the RGB. And if the saturation is 1, happens if the mean is very small to the max. If this is 0, mean is very small to the max, you are far on the boundaries of the disk, actually. Okay. How much one color is more dominant than the other. So I find it less annoying the more I looked at it. It started to make sense. Okay. And there are formulas, I don't specify them, of going the opposite way. Okay, let's start to think about, yeah.
Back with the conversion for HSV, why is it undefined if the max equals 1?
Because I cannot, it means that it's gray.
So it doesn't matter, so it just doesn't bother finding.
I will specify it over here. I will specify the intensity that doesn't depend on what the max is. The intensity is determined by the max, essentially. And actually, I've seen these formulas that determine the intensity as just the max, or determine the intensity as the sum of the whole three. And that would be how strong the pixel is illuminated. Great question. But how much does it, how much can I specify a color as, yeah, it's gray, but a bit tending to green, a gray, but a bit tending to blue, and so on. The more extreme I am, the larger the saturation I am, the more easier, I guess, for me to say that's a color that I see. It's more pronounced. But it's very hand-wavy, and I'm sure that Kobos, that made his PhD on colors, can give a much better explanation over here. So that maybe the point of me to say that my knowledge is limited over here. Okay, so talking about something that I'm always debating, should I go through it or not? Because it's important, and it's important as general knowledge. I will not argue that thinking about image as signal is absolutely necessary to do good anti-aliasing. So I would skip it if the only purpose of it would be anti-aliasing. But because I see other parts that we are using it, let's think about it. So we are thinking about the image as a sampling process. There is an email, when I think about a camera, digital camera, we'll think about an image that is changing and has value for each point, not only each pixel, but every point, any sub-pixel resolution that you can think of, and it will give you a color at this point, the RGB value at this point. So you're asking, I took a picture, there is some region in the 2D plane that I take the picture from, and the range is a set of possible values of, say, RGB, or whichever coordinate system that you want to ask. But the main question here is, what is a pixel? We'll make it into a more philosophical way of what is a pixel. So just to show you, if you didn't read, the space of the colors value is RGB will be, if the camera will produce an RGB file, then that's what I expect the sampling to produce. But again, if I'm only sampling from the picture, what do I do? I have the whole picture, which I can think in each one of the channels as something that changes continuously. The real image that we are trying to give back to reconstruct then in the rendering. But when I take a picture of it, all I did was to sample it at certain point. So a pixel just does a sample of the whole function, which is in 2D function, intensity, RGB, in all three functions, and my pixel that now I can think about as a single pixel, where what I did is sampling, but the color at the middle of the pixel. Or if you want to go fancy, the value of the pixel will be either a sampling point in the color of the pixel, or if you want to go more fancy, then you actually account light on some area inside the pixel and integrate over it. But either way, there are details that I might not be able to reconstruct because my sampling rate is badly behaved. Okay, so just to do this strange ECE-like attempt to call it a continuous domain where the image will exist versus we have a discrete domain at which we reconstruct, sample the original image, and then use this data to reconstruct the original image. Okay, and just to give you we'll go back to these slides. We'll go back to these slides. But this is a camera. People see problem with sampling? People, I wanted to get to this video to explain what's a problem with sampling issues over here, right? Why does it look to us that it's moving backward? Sorry. All you see is a balloon over here that push wings into these wings, and it rotates. And now you notice that it starts to rotate backward. Well, it doesn't, but it looks like it starts to rotate. And then it looks like they are barely moving. Why? What's the explanation? You all know it, but somebody might vocalize it.
Because at the frame rate we're looking at, the difference between frames,
We sample now the image in time, not in space, but if we sample it and at one particular time, and then our next frame happens exactly where the things moved an integer number of times, like we moved from one to the next one, it will look like it didn't move at all. So that's, we are, in short, we are not sampling the signal densely enough. Say again?
I wanted to see the whole thing.
Oh, you. Okay, it's not very long.
Apparent changes of direction and speed that deviate from the true rotation are stroboscopic effects caused by temporal delays. Aliasing occurs in video when the sampling rate of the camera interacts with a rotating object. This is the wagon wheel effect.
So you will ask, is this issue happens only with time, or do we also care about it if we are only using graphic images? Yes, it does happen. What happens here is that I shrink by shrinking the image down, by scaling the image down, I sample the original image by sample every 4th pixels. If now the image is much larger, and now increasing it, you see the aliasing method, another image of aliasing. So we'll show methods of reconstructing what the signal might have been earlier. And aliasing would be related also to images as this. There are no really waves over here. There is no, that's how this wall looks like with more sampling. You don't have more dark bricks and whiter bricks. And then we'll talk about convolutions. The cool things with convolution is that it's really a big tool that will help us take images that are kind of blurry, counterintuitively makes them even more blurry by convolution, take the difference between them, then miraculously will show us where the boundary of the image is, add it to the original image, and the original image is much sharper than the origin. That's another result of convolution. Or looking at high D images that I mentioned, where you have very dark area and very illuminated area, and without further tweaks, just sending the raw data to your computer. Either this would be completely dark, or this would be completely illuminated, but you cannot do, or this would be completely waved and fully saturated way beyond the, and don't see any details of the sky, but you cannot win both of them unless you play with HDR techniques that go through convolution. Okay, thank you.